Hello students, today I am going to discuss another problem based on the oscillation of uh, simple pendulum in a liquid of density rho. So the question is, if the bob of a simple pendulum having density rho b is made to oscillate in some liquid of density rho l, then find the frequency and time period of oscillations of the pendulum. Okay, so for this let me draw this simple pendulum first. Okay, suppose this is my simple pendulum. This is the bob. It is suspended by a string of length L. Okay, and now this bob or pendulum is dipped in a liquid of density rho L, and then it is made to oscillate inside the liquid of density rho. Okay, so density of the liquid is rho L. Now this I will make it oscillate. I will allow it oscillate. I'll bring it here and I will uh, release it from this position. Then it will perform SHM about this mean position. Okay, let me name it. This is the mean position or equilibrium position, because the net force on this bob at this particular position is 0. F net equal to 0. Okay, F net equal to 0. Now what are the forces acting on this particular bob? One is the weight of the bob. Okay, one is the weight of the bob here, weight of the bob, and upward, the upward direction, this force of buoyancy, and along the string it is the tension force, right? Okay, now weight of the bob is given by mass of the bob into g. Since rho b is the mass of the rho b is the density of the bob is given, let vb is the volume of the bob. Okay, volume of the bob. So mass of the bob will be rho b into vb into g. Okay, then force of buoyancy will be equal to mass of the liquid displaced into g, right? So what is the mass of the liquid displaced? It is rho into L, means density of the liquid, into volume of the body submerged. That means here body is the bob, so volume of the bob into g. So these are two forces acting, WB and FB. WB means weight of the bob and FB is the force of buoyancy on the bob due to the liquid of density rho L. And another force is there, is tension in the string. Okay, so now because of all these forces, there will be torque acting about the point O, which will bring it towards the mean position. Okay, and it will perform SHM about this mean position. Okay, so let me find out the torque of these all forces about point O. Okay, so net torque will be equal to tau net is equal to torque due to weight of the body plus torque due to force of buoyancy plus torque due to tension force. Okay, now first I will find out the torque due to weight of the body. Okay, now according to the definition of the torque or mathematical formula, that is, it is R cross F, right? Now the force is weight of the body and the R is the position vector of point of application of force with respect to the point of rotation. Now this O is the point of rotation here, and point of application of force is B, suppose at this particular position. Okay, so this is your L. Okay, let the length of the string be L, then this R vector magnitude will become L. So direction of the R vector will be along this direction, because this is the position vector of point of application of force, that is the point B with respect to point O, point of rotation. Okay, this is your point of rotation. Okay, so R is your, from this we have the definition according to RF sin theta n cap, where sin theta or theta is the angle between the position vector and the force vector. Okay, so now R is your L, F is your weight of the body, that is given by rho b Vb into G, okay, into sin theta. Now from the cross product rule, its direction is like this. Okay, it will rotate like this. So if it rotate like this, then its direction is into the screen. Okay, in the screen. So let me take that particular direction be along the z axis, that means k cap, positive direction k cap. Let me take this. Then torque due to force of buoyancy is again R cross F. R is again this vector from this point to this point, point of application of force, but now the force is this one. Now the force is along the upward direction. Now previously it was RF sin theta, where theta is the angle between the R and F. This was your force weight, then this was the R vector, okay, and the angle between them was theta. Now angle between these two vector, this is your force vector, force of buoyancy, then angle between R vector and force of buoyancy vector is 180 degree minus theta, right? 180 degree minus theta. So what we will write here is that L, because R vector is your this vector, so magnitude of R vector will be L. Now F is your force of buoyancy, then sine of 180 minus theta, because angle between these two force vector is two vector, means position vector and force vector is 180 minus theta. So we will have L, what is the force of buoyancy from this? Rho L into Vb into G, right? Then we'll put it as sine theta, because sine 180 minus theta is sine theta. Now this will have R cross F, since in this R cross F, so we'll have this rotation like this, okay, anti-clockwise. So it will have the direction out of the screen. Okay, so let me take that as minus k cap, minus k cap. This is equation number 1. Equation number 2. Now torque due to this tension force, okay, tension force is equal to 0. Torque due to tension force is equal to 0. Why? Because this tension force passes through the point of rotation, and as all of you know that this, if a force passes through the point of rotation then the torque about this that particular point due to that particular force is equal to 0. Okay, that's why torque due to tension force is 0 here. Okay, now if we put this in this equation, in this net torque equation, tau net individually, okay, we will get L rho b Vb into G sin theta minus L rho L Vb G into sin theta k cap, right? So now this can be written as tau net as L VBG is common, so rho b minus rho L into sin theta. Okay. Now if sin theta is small, then we can write sine theta approximately as theta. Then this equation, Townend equation, will become L VBG rho v minus rho L into theta. Okay. Now for torque net, we can write it as I into alpha. Okay. L VBG rho v minus rho L. But this I is your moment of inertia, right? This I is your moment of inertia. About the point of rotation, right? About the point of rotation. Now what will be the moment of inertia about this point of rotation? Mass of the bob is m. Okay. Then perpendicular distance from this is your L. So it will be ml square, right? Ml square. So in place of I, but we can write it as ml square, right? Ml square. What is the m? A mass of the bob, right? Alpha ml mbl square alpha L VB G rho v minus rho L into theta. Okay. So what will be alpha then? VB L G rho v minus rho L into theta divided by MVL square. So for this we can write LL got cancelled. For mass of the bob, but we can write density of the bob into volume of the bob. Okay. So VBG rho v minus rho L rho v VBL. This VB where VB got cancelled. So we are left with G by L into rho v minus rho L by rho v. Overall, we are getting it alpha equal to 1 minus rho L by rho v into G by L. Okay. Now for alpha, what we can write? It is d2 theta by dt2. Okay, alpha is the angular acceleration here. So we can write the d2 theta by dt2, second order differential with respect to time for this angular displacement. So it is 1 minus rho L by rho v. Oh, here 1 theta was there. G by L into theta. Okay, theta. So in this equation, we need to put one negative sign, because this negative sign will indicate that the force is towards the mean position, right? The force is towards the net force is towards the mean position. So we have a negative sign here. Significance is that this force is towards the mean position. So from this we will have d2 theta by dt2 plus, bring this here, omega square theta equal to 0, where omega is equal to root over 1 minus rho L by rho v into G by L. Okay. So if we compare this is the second order differential equations for the simple harmonic motion. Okay. And if we compare this with this equation, then we get omega is equal to this one. This is your angular frequency of the oscillation. Angular frequency of the oscillations of the bob. Okay. So what will be the time period then? The time period can be given as t equal to 2 pi by omega, right? So it is 2 pi root over L by 1 minus rho L by rho B into G. Okay. So this is the time period of oscillation of the simple pendulum when it is made to oscillate inside a liquid of density rho, where rho L is the density of the liquid and rho B is the density of the bomb, material of the bomb. Okay. So this is all about this uh, question. So I hope all of you have understood this problem, and if you have any question, then feel free to ask me. Now, based on this particular concept, based on this solution, okay, this is the problem and this is the particular solution, and based on this solution there is one problem asked in JEE 2019, I think JEE means 2019, and this is your question, and I'm giving you it as homework. So please try to do it at your home. This is asked, this was asked in JEE Main 2019. Okay. So try to do this problem based on these particular video solutions that I have provided you. Uh, and I will bring a solution of this particular question in my next video. Thank you. Thank you so much.